Okay, so in this tutorial, we'll see how to carry out regression when you have categorical predictors. So the data set that we'll be using today contains ratings of various wines produced in California. We'll just focus, as I said, a lot of these tutorials are basically meant to let you know how to use R to produce the relevant output. And we're not really trying to solve questions or answer questions of interest with any of these examples. So as usual, let's read in the data that we have, the wine data. So be sure that you've downloaded the script and the associated PDF as well as the data set. So let's run this. And one thing I always say, it's probably useful just to take a look at how the variables are recorded. So we're going to look at how quality depends on a couple of different factors, right? One being flavor and the other being the region in which the wine is produced. So if you take a look at region, right, it's recorded as numerical values between 1, 2, and 3. But these are actually just numerical values that they use to represent different regions. So 1 means the North region in California, 2 means the Central region, and 3 means Napa Valley. So when you get data, very often the person collecting the data may not realize that they might want to save some typing and using numbers and use numbers to represent values in a categorical variable, but they don't realize that that kind of actually gives you an extra step that you need to do when you analyze the data. So when it's recorded numerically like this, R will basically think that the variable region is quantitative, so they might think that it makes sense to add them up and take the average of them. So a few things you could do just to check, right, is you can use the function isNumeric and the name of the variable to see, and if it says true means R is viewing this variable region as a quantitative variable. So if you want R to treat it as categorical, we could use the function factor. Factor is just another word that some people use for categorical. So we just type that in, and if you want to confirm whether R treats it now as categorical, we just use isFactor, and if it says true, that means it now views the variable region as a categorical variable, right? And it wouldn't try to add the values up and take the average. So that's one thing you could do. Another thing you could do is to check how what coding scheme R uses. So we could use the contrast function, right? So it basically tells me that the reference class is the first region number 1. So they are basically creating two indicator variables, one for the second region and one for the third region. So now you notice that we are still using the numbers, right, as labels for the different classes. I personally like to give descriptive names to the levels for each category, for the categorical variable. I really don't like the numerical values because it's confusing. So one way to go about doing it, right, you could name it using descriptive names. So the levels function tells you, okay, right, that the levels are level 1, level 2, level 3. So I want to change these to descriptive names. So I could use this line of code to say that the first class I want to call it North, the second one I want to call it Central, and the third one I want to call it Napa. Right, so levels region, and I basically give the descriptive names. Right, and I use the contrast function to see, okay, now the North region is going to be the reference class, right? The first indicator variable is for the Central region, and the second indicator variable is for the Napa region. So that's what you could do. Now, what you could do also is to change the reference class. I typically do this if there's a particular class that I'm most interested in comparing with everything else. So for example, maybe I want to set Napa as the reference class. To do that, I can use the relevel function. Right, relevel my variable, and I put Napa as the reference class. So if I do that and I run the code, this contrast function again, I see that now my Napa Valley is now the reference class, right? So one indicator for the North, one indicator for the Central region. So yeah, so those are some things you could do, right? So just a few additional things that you could do if a categorical variable is recorded using numbers, how to have R treated as a categorical variable, and how you could give descriptive names, and how you could change the reference class. Another thing that will be useful when you're analyzing, when you're using a regression model with categorical data is to basically create a scatter plot and create separate scatter plots for each class of your categorical variable. So how could we do this? So in this case, we are going to create scatter plots, a scatter plot for the response and the quantitative variable, and we're going to use different colors and symbols for each region. So to go about doing that, basically what I'm going to do is to ask R to separate or to subset the data set right into each of the regions. So I could use a subset function. So A1 is going to just look at the data set where the region is equal to 1. So in this case, when you use region equal to 1, you have to use the original label. And because we changed the region to a categorical variable, we have to put the open and close quotes for it. So I'm going to ask R to create 3 different data sets, A1, A2, A3, and they basically are going to be the data from regions 1, 2, and 3 respectively. Then I'm going to ask R to create 3 separate regressions using each of these subsets. So regression 1 is basically the regression of the response against the quantitative predictor just for region 1, and then regression 2 is for region 2, and regression 3 is for region 3. Right, so this is basically, I basically ask R to create 3 separate regression lines, one for each region. Now, to create the plot, so I'm going to shrink this a little bit and maybe expand this a little bit. What we're going to do next is to create a scatter plot with different colors and symbols for each region. So let me just run this first line over here. That's our usual scatter plot, right, of the response against the quantitative predictor. It's not separated by the different regions yet. So what I could do is I could use different, so this points function basically says I want to do it for A2, right, which is for region 2. And I'm going to use plotting character. So PCH means plotting character. I'm going to use a different symbol rather than the black circle. And I'm going to use the red color for that, for the second region. For the third region, I'm going to use plotting character 12 and blue for that, for the region 3. So let me just run those 2 lines of code and take a look at the picture that we have. Right? So we see the blue plots. Now these represents region 3, and the red triangle represents region 2. Now the next thing I could do is to overlay the 3 separate regression lines, right? So AB line is basically the regression line for regression 1, line type 1, and then the regression for the second one using red, and the third region using blue. Right, so let me overlay those 3 lines, and I can have, so this is my scatter plot, right, which the black one represents region 1, the north region, red represents the central region, and blue represents the Napa region. So again, one thing that's missing is probably a legend. So we could use the function legend to create a legend. So legend, and then the first one is saying where in the plot you want the legend to be. So I'm going to put it on the top left. And my regions are North, Central, and Napa. So for each region, right, if you notice for each of these plots, there's a line type, LTY is line type. There is a plotting character and a color for each region. So North region is the first one, right, which I didn't assign. So the default is line type 1, plotting character 1, and black. That's the default. The second region, Central, I use line type 2 for the second regression. I use plotting character 2, and I use the red color for its color. So basically it's saying, right, for central region, line type 2, plotting character 2, red. And so you just want to be very careful, right? Be sure the order is correct. So the third one obviously is for the Napa region. And you apply the legend, and let me go back to the graphics, and we can kind of see with this plot, right? We can see 3 separate regressions, North, Central, Napa, clearly labeled. And so we can kind of see, right, that these 3 the relationship between the flavor and the quality rating is a positive relationship. The slopes visually look different, although they are not that different, right? So we wonder whether these are the slopes in the sample, whether these are whether they could actually possibly come from the population where the slopes are all the same, right? Is this difference that we see in our sample just due to random sampling? So that's where we want to carry out some hypothesis tests to see if the slopes are actually all the same or not. So when you think that the slopes look different, then we want to consider fitting an interaction, right? Because when the slopes are not the same, that means it's possible that there's an interaction between the predictors. So I'm going to fit a regression model where I'm going to fit an interaction. So to fit an interaction between your predictors, we're using this asterisk over here, or like the multiplication sign instead of a plus sign. So I'm going to fit that model. I'm going to call it result. And we kind of notice the following, right, is that if we look at the interaction terms, they look like they are insignificant. So it means, well, we could potentially drop them. So I'm going to compare this model with the model with no interaction. I'm going to call that reduce, and I'm going to carry out like a partial f-test to see if I do not need the interaction terms. So in this case, my f statistic and my p-value is pretty big, greater than my significance level. So this tells me I don't need the additional interaction terms in the model. So I could consider the simpler model without any interaction. So what we see in our sample, right, even though they look a little bit different, they could potentially come from a population where the slopes are all the same. So now that we're going to consider that we're going to use the reduced model, right, the model with no interaction, to carry out diagnostic plots or to check the regression assumptions when you have categorical variables are almost the same. So I'm not going to run all these lines of code because you already have done this a number of times. You could create a residual plot, ACF plot of the residuals, as well as a QQ plot of the residuals, and we're looking for the same features. Now, when we have a categorical predictor, there's an additional assumption to check, which is whether the variance of the response variable is the same for every class of the categorical predictor. So a few ways to do that. One is to create a box plot of the response for each region and just visually see if the spread of the response looks the same for each region. So visually it looks the same, right? But again, it's just a visual. So perhaps we want to perform some sort of hypothesis test to check that. So that is the hypothesis test that we want to use is what we call Levene's test of equality of variances. And this function can be found in the lawstat library. So I've already installed this, so I'm just going to type in library lawstat to load it. And then I'm going to use the levene.test function, right? So the first one is the response variable and then the categorical variable. So let me run this. So the null hypothesis is saying that the variances are the same, and the alternative is saying that the variances are not the same for all classes. So p-value is pretty big, so we fail to reject, right? So, right, it looks like that the equality of variance assumption is fine. So now we know that's fine, so we can continue with our analysis of this model with the categorical predictor with no interaction, right? So I can kind of take a look at the regression output to see the estimated coefficients for each of the predictors. So we know the interpretation of, say, this coefficient, right? So this is the coefficient for the dummy variable for north. It's comparing the north region with Napa Valley, right? And it's significantly different from Napa Valley. This one is the indicator for central, and the interpretation of this is to compare, right, whether the central region is significantly different from the Napa region when we control for flavor, right? So we know that we can compare these two directly with Napa Valley, right, with the reference class. Now, one thing that you might also be interested in, well, what happens if I want to compare the north and central region, right? I have to perform a few other things. So one way to do that is to perform what we call Tukey's multiple comparisons. So with that method, you're basically comparing all possible pairs of classes. Now, to do that, we're going to use this function called GLHT. It's basically like general linear hypothesis test. It is found in this library called multiple comparison, or multcomp for multiple comparisons. So let me just load that library. And to carry out the test, we use GLHT using our reduced model, and I'm going to use the Tukey's multiple comparisons for the variable region. So let me just run that, and I'm going to summarize the GLHT function. So this gives me all pairwise comparisons, right? So since I have 3 levels, there are 3 possible pairings. One is north with Napa, and whether that's significantly different from 0, so p-value is small, it is significantly different from 0, so they are different. I want to look at central with Napa, that's significantly different, and central with north, that's significantly different as well. You could also see what direction the difference is, right? So north minus Napa, that estimate is negative, which means Napa's quality rating is higher, right? Because north minus Napa is negative, means Napa has a higher average rating. Central minus Napa, negative, so Napa has a higher average rating. Central minus north, negative, north has a higher average rating. So that's what you could do, right? In what R could help you do. Now, obviously, what could happen is you might want to calculate some of these by hand. If you want to, what you need are the coefficients for your model, right? So we have that. And we also need the variance-covariance matrix of your model. So that can be found using the vcof function. And I'll show in your notes how to do this calculation by hand if you want to use the hand calculation for this.